Hello everyone, welcome to this video lecture of this course finite element method. So this is the module number 3 which we are continuing, and this module 3 it basically deals with the two-dimensional scalar variable problems, and today it is the fourth and last lecture of this module 3. So in this module earlier we have discussed the concept of the finite element modeling for these two-dimensional scalar variable problems, where we have discussed in details the concept of discretization and the numbering of nodes. Next, we have discussed different formula regarding the stiffness matrix, then shape function, then strain displacement matrix, and how to solve various complicated numericals based on those different formula. So there we have discussed around 5 or 6 problems, and we have seen that the matrix operation such as the matrix addition or matrix multiplication, these are very much important. Okay, so these are the things for the structural analysis problems we have discussed till now. So today we will discuss the non-structural concept, that is the thermal problems for this two-dimensional scalar variable problems. So today also we will see that considering the thermal problems, that is the heat transfer, how the formulas are going to change for stiffness matrix or shape function or the interpolation function, as along with the displacement functions. And based on all these different formula, we will discuss different numericals for the thermal problems. Okay, so let us start this lecture. So the first topic that we will discuss, it is the heat transfer in two dimension, considering which is the thermal problems. So first we will see the shape function derivation for heat transfer in 2D element. So in this diagram 3.16 you can see there is a 3-noded triangular element given, and all the 3 nodes are having their displacements in x and y direction. The coordinates for these 3 different nodes are given. So we are considering this triangular element because its derivation, it is the simplest among the available two-dimensional elements. So the nodal displacement for these 3 different nodes of this triangular elements, these are u1, u2, u3, v1, v2 and v3. So that means the displacement matrix, that is U, this is a column matrix of U1, U2, U3, V1, V2, V3. Now since this triangular element, it has got 2 degrees of freedom at each node. So the total degrees of freedom, this is 6, hence it has 6 generalized coordinates. Now the formula for U, it is alpha 1 plus alpha 2x plus alpha 3y, and the formula for V, this is alpha 4 plus alpha 5x plus alpha 6y. So these two equations we have considered here for the displacements u and v, which are equation number 3.51 and 3.52, and here alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 and alpha 6, these are global or generalized coordinates. So if u is alpha 1 plus alpha 2x plus alpha 3y from equation 3.51, so in that case u1, it will be alpha 1 plus alpha 2x1 plus alpha 3y1. Then u2 is alpha 1 plus alpha 2x2 plus alpha 3y2. And in this similar manner we can write the equation for u3, which is alpha 1 plus alpha 2x3 plus alpha 3y3. Now for these 3 different displacements of u1, u2 and u3, if we write these equations in the matrix form, then we are getting this matrix, which is a column matrix of u1, u2, u3. This is equals to a 3 by 3 matrix, multiplied by a column matrix of alpha 1, alpha 2 and alpha 3. So this is the matrix form of the displacement function equations of u1, u2 and u3. So that means the column matrix of alpha 1, alpha 2 and alpha 3, this is equals to the matrix inverse of this 3 by 3 matrix multiplied by the u1, u2 and u3, which is our equation number 3.53. So now we have considered this 3 by 3 matrix. This is D. So D inverse, it will be Ct divided by the determinant of D. So this is from our general concept of the matrix operation. We know this part 3.54. So first, to find the inverse of this D matrix, we need to first find the cofactor of matrix D. So the cofactor C11, it is now x2y3 minus x3y2. So the concept to find the cofactors of matrix, these are known to us. We have studied in engineering mathematics all this concept of matrix operations. So I am not going to discuss the matrix inverse or the cofactor concept here. So next, C12, this is equals to y2 minus y3. Then C13, C21, C22. So that means all the different cofactors we need to find here. Now if we put all these cofactor values in the C matrix, then we need to perform the C transpose. So this is our equation number 3.55. Now the determinant of this matrix D, this is equals to equation number 3.56. So so we have found out the determinant of this matrix. So now we need to substitute the C transpose and D in the equation 3.54. That means if we go back to the earlier equation, so till now we have seen that D inverse is Ct by D. So Ct, it is the transpose of the matrix which is formed taking the cofactors of the matrix D, and that one we need to divide with the determinant of the D matrix. So now if we put these values here, so we are getting this mathematical representation, a 3 by 3 matrix multiplied by the determinant of that matrix D divided by the determinant of the matrix D. Now we need to put that value here. So in this way we are getting the equation number 3.57, so which is the mathematical representation of the column matrix consists of alpha 1, alpha 2 and alpha 3. So it is a 3 by 1 matrix. Now the area of the triangle, it can be expressed as a function of the xy coordinates of the nodes 1, 2 and 3. So first, now we need to find the area of the triangle. So the formula, it is half multiplied by a 3 by 3 matrix. So we need to find the area in this way. That means the determinant, it is now half multiplied by the determinant of this matrix. So that means 2a, this is equals to x2 minus y, x2 y3 minus x3 y2 minus x1 into y3 minus y2 plus y1 into x2 minus x2. So this is our equation number 3.52, which is the equation for the area of this triangular element. Now we need to substitute this value or the equation of this area, that means the value of 2a from equation number 3.58 we need to put in this earlier one, it is in equation number 3.57. So finally we are getting the equation number 3.59 and 3.60. So in this equation number 3.60, here we have considered A1, A2, A3, B1, B2, B3 and C1, C2, C3 by considering the different coordinates for the nodes or the nodal points of the triangular element. Now from equation 3.51 actually we have seen that the mathematical expression of the displacement function u is alpha 1 plus alpha 2x plus alpha 3y. Now we can write this equation in the matrix form as u equals to the row matrix of 1xy multiplied by the column matrix of alpha 1, alpha 2 and alpha 3. Now if we substitute the value of alpha 1, alpha 2 and alpha 3 from the earlier equation, then we can write the equation of the displacement function u equals to a row matrix of 1xy multiplied by 1 by 2ic multiplied by 3 by 3 matrix multiplied by a 3 by 1 column matrix of u1, u2, u3. Next we can perform the matrix multiplication here, and finally we are getting the equation of the u as a row matrix, it is 1 by 3 matrix multiplied by a 3 by 1 matrix of u1, u2, u3. Now in this above equation we can consider some parameters as n1, n2 and n3 for the row matrix multiplied by a column matrix of u1, u2, u3. So this equation 3.61 is a very important equation which we need to remember to solve different numericals. Now what are these n1, n2 and n3? These n1, n2 and n3, these are the shape function where the n1 is a1 plus b1x plus c1y, then n2 is a2 plus b2x plus c2y, then n3 is a3 plus b3x plus c3y divided by twice a. So these are the formula of n1, n2 and n3, these shape functions. Now here a1, b1, c1, these are having their own values which you can see in this slide. In this 8 number slide we can see the value of this a1, b1 and c1 which are in terms of the coordinates of the triangular elements. So in the similar manner we can write the formula of the displacement function v, that is n1, n2 and 3 row matrix multiplied by a column matrix of v1, v2 and v3, which is our equation number 3.62. Now if we assemble this equation 3.61 and 3.62 in matrix form, then we are getting the displacement function u equals to a column matrix of u and v, which is a 2 by 6 matrix of the shape function, that is n1, n2 and 3 multiplied by a column matrix of the u1, v1, u2, v2 and u3, v3. So this is the final equation of the displacement function, where the value of the shape function, that is n1, n2 and n3, we need to remember, like n1 is a1 plus b1x plus c1y divided by twice a. Again, what is the formula of a1 and b1 in terms of that coordinates x1, x2, y1, y2, that we need to remember also to solve the different numericals. Let us next discuss the stiffness matrix and load vector for heat transfer in two-dimensional element. Till now we have seen that the triangular element diagram which is given here, this is actually the basic element for solution of two-dimensional heat transfer problem. So consider such three-nodal triangular element with nodal temperatures T1, T2 and T3, which we can see in this diagram 3.17. At the nodes or nodal points 1, 2 and 3, the nodal temperatures are considered T1, T2 and T3. And the temperature function Txy, it is actually given as N1 T1 plus N2 T2 plus N3 T3. Now from this equation, if we consider the conduction and convection heat transfer, then after several steps we will get this equation number 3.74, which is the stiffness matrix for conduction. Now there is a lengthy derivation for this stiffness matrix of conduction, so we need to only remember this formula 3.74 to solve the numericals, which we are getting the stiffness matrix for conduction, this Kc, which is K by 4A multiplied by this 3 by 3 matrix. Next we need to actually find the stiffness matrix for convection, and finally we need to add these stiffness matrices of conduction and convection to get the final stiffness matrix for this two-dimensional heat transfer. So that means the total stiffness matrix for this heat transfer, it will be the summation of the stiffness matrix for conduction plus the stiffness matrix of convection. Now the stiffness matrix for conduction we have seen in figure in equation 3.74. Then for stiffness matrix of convection we are having this data, it is H12 S12 divided by 6 multiplied by 3 by 3 matrix, then H23 S23 by 6 multiplied by 3 by 3 matrix plus H31 S31 by 6 multiplied by 3 by 3 matrix. So this second, third and fourth part, this is the stiffness matrix for convection heat transfer actually. So the final stiffness matrix for two-dimensional heat transfer, which is the summation of conduction stiffness matrix and convection stiffness matrix, so it will be the equation of, it is represented by equation number 3.87. This H and S, these are the convective heat transfer, and the S is the surface, that means it is the length of the side 1 2. This is the convection from the side 1 2. So in this similar manner we need to calculate the maybe convection or the length of that side of the triangular element. Next, the formula for the force vector or load vector F equals to, we need to also remember that the force vector for two-dimensional heat transfer element, it is in general form we can write F1 is integration Q naught and matrix transpose in dV. This is equation number 3.88. So are several steps to find the force vector equation. So we need to only remember the final formula for F1, F2 and F3 for these three different force vector or load vector. So the F1, this is equals to Q naught A by 3 multiplied by a column matrix of 1 1 1. Then F2, this is Q12 S12 by 2 multiplied by column matrix. Then F3 is H12 T alpha S12 by 2 multiplied by column matrix. So these three equations for force vector or load vector we need to remember. Now let us discuss one numerical based on this concept of the heat transfer for two-dimensional elements. The question states that we need to compute the element matrix n vectors for the element which is shown in this diagram when the edges 2, 3 and 3, 1 experience convection heat loss. So in this diagram we can see that one triangular element it is given and the coordinates for its three different nodes, these are also given. Then the convective heat transfer coefficient, its value is given T alpha, the temperature is given 40 degrees centigrade for the two different sides, it is for side 2 3 and for side 1 3 of this triangle. The value of H and T, these are given. So let us first write the coordinates for the nodes given in this numerical. It is also given the thermal conductivity, it is K equals to 60 watt per centimeter Kelvin, and Q naught, it is 50 watt per centimeter cube. Then corresponding to node 1, we can write x1 u1, this is 4,6. Then corresponding to node 2, x2, y2, it is given 8, 10. And corresponding to node 3, x3, y3, it is 12,8. Now the convection sides, that is side 2, 3, here we will be having H23, it is given as 10 watt per centimeter square Kelvin and temperature is 40 degrees centigrade. Then for the other convection side 1, 3, the H13, it is given 15 watt per centimeter square Kelvin and the temperature is 40 degrees centigrade. So we need to find the element matrix Kc and Kh and force vector. So these are the things which are given in this numerical, and based on these values we need to find the element matrix Kc and Kh and the force vector. So the formula for this conduction heat transfer we have seen earlier. The formula is K by 4A multiplied by this 3 by 3 matrix. So first we need to find the area of this triangle, which is half multiplied by 3 by 3 matrix, where we need to put the value of the coordinates for the three nodal points. So after putting all the required values, we have calculated the area of the triangle as 12 centimeters square. Next we need to find the value of this B1, B2, B3, C1, C2 and C3, which are represented in terms of the coordinates. So we need to remember the value formula for this B1, B2, B3, like B1 is Y2 minus Y3, B2 is Y3 minus Y1, then C1 is X3 minus X2. So in this way we need to remember the formula for this B1, B2, B3, C1, C2, C3 in terms of the coordinate values. And finally we need to find the values of these different parameters. After finding the values of this area and the parameters like B1, B2, C1, C2, all these things, we need to put all these parameter values in the stiffness matrix of conduction. So finally we are getting the stiffness matrix for the conduction heat transfer, which is our equation number 1. Next we need to find the stiffness matrix for convection. So here from the two sides only of this triangular element the convection heat loss is occurring, so we'll consider those two sides only. In the formula for those two sides of this triangle we need to remember and we need to implement here. Now the H13 and H23, that is the coefficient of convection heat transfer for the side 13 and 32, which you can see here for the sides 1 3 and 3 2, the H value, these are given as 15 and 10 watt per centimeter square Kelvin. So we can directly put this H value, that is the coefficient of convective heat transfer, directly in this equation. Now we need to find the value of S13 and S32. So these are actually the length of the H13 and length of the H32 respectively. So S13, its formula can be written as root into x1 minus x3 whole square plus y1 minus y3 whole square. So if you put the value of the coordinates, then we will be able to calculate S13 as 8.25 centimeter. Now in this similar manner, we can calculate the value of S32, which is 4.47 centimeter. If we put the value of all these H and S in this equation of the convective heat transfer coefficient, then finally we are getting a 3 by 3 matrix as equation number 2 for the convective heat transfer coefficient matrix. So these are the values that we have calculated till now, Kc and Kh. That is the stiffness matrix for conduction heat transfer and stiffness matrix for convection heat transfer. Next we need to calculate the force vector. So here the formula of the force vector F1, it is Q naught A by 3 multiplied by the column matrix of 1 1 and 1, which is at side S1. So here within bracket it is written heat flow with the boundary element. Now the formula for this force vector we have discussed earlier, and we had to actually remember these three different formulas for F1, F2 and F3. The derivation part is not required, you need to only remember the formula for the force or load vector. So the formula for F1, it is Q naught A by 3 multiplied by column matrix. So we can directly put the value here and we can find the column matrix for F1. In the similar manner we can find the column matrix for F2. There's no boundary heat flux specified here, so F2 is 0. And for the column matrix F3, then we can calculate the F3 also, which is we are getting as a 3 by 3 matrix. So this is the final result that we have present here. The stiffness matrix for the conduction heat transfer, it is Kc, then the stiffness matrix for the conduction heat transfer, it is Kh, and the force vector F1, F2 and F3 we have also written here. So this is the procedure by which we have calculated these element matrices and the force vector, considering the thermal problems for the heat conduction. So we need to actually remember the different formula for this conduction and convection heat transfer, stiffness matrix and the force vector. So a lot of matrix operation are required while solving such numericals, and the formulas also, these are not very easy, so we need to practice such numericals so that there will be no more mistake and we can remember such formula. Let us discuss the next numerical. So we need to find the temperature distribution in a square region with uniform energy generation, which is shown in this diagram. We need to assume that there is no temperature variation in the z direction. It is given thermal conductivity, then it is 10 centimeter, then temperature is 50 degrees centigrade, and Q is 100 watt per centimeter cube. These are the things given. So we need to find the temperature distribution. So first we have converted the given, we have divided actually this given rectangle in two different triangular elements, and for these two different triangles we have found their coordinates for the nodes. Now let us consider the element 1. So here we are having the coordinates, so we can easily calculate the area of this triangle, and the formula it is known to us, so we have calculated the area which is 50 centimeter square. Then we need to calculate the length at side 1 3, so the formula is also known to us, so we can calculate the length 1 3. Next we need to calculate the value of the b1 b2 which are b3, then c1 c2 c3, so which are related to the coordinates of the nodes. Then finally we need to put all this value of the area and b1 b2 c1 c2 then b3 c3, all these things in the formula of stiffness matrix for the conduction, and finally we are getting this representation of the stiffness matrix for conduction heat transfer. Next, for the element 2, similarly we can calculate the area of the triangle, it is half into it, so the area we are getting is 50 centimeter square. So we can directly use this formula because now we know the length of b and h, so we can directly put this value and we can calculate this a2. Next, again in the similar manner we need to find the value of this b1 b2 b3 c1 c2 and c3 which can mathematically represented in terms of the different coordinate values. And finally if we put these values in the stiffness matrix for the conduction, then we will be getting this k2. If we assemble these two matrices, then we will get a 4x4 matrix for the stiffness matrix of the heat transfer. Next, to find the load vector, the formula of the load vector F equals to QA by 3 multiplied by column matrix. So in case of the element 1 and element 2 we need to find the load vector, so that means in case of the element 1 you can write f1 f2 f3, this column matrix, this is QA by 3, so the value of the Q and A, these are given, that means Q is given in the numerical and the value of the area for this triangle we have calculated. So we can find the value of this load vector for element 1, and in the similar manner we can find the load vector for this element 2. If we assemble this load vector, then we will get a 4x1 matrix here, column matrix. Next, we need to find the global matrix, and the formula it is the multiplication of K matrix into T matrix. Now for the temperature distribution at node 2 and 3, this T temperature T equals to T2, T3 and T4, these are equivalent, which is 50 degrees centigrade. So that means if we put the value of this F, K and T matrices now in this earlier equation, then from that we can perform the matrix multiplication and finally we can calculate the value of the T1. So the temperature distribution we can represent in the matrix form, where we can see that the T1 is 160 degrees centigrade, T2 is 50, T3 is 50 and T4 is also 50 degrees centigrade. So these are the concept of the heat transfer in case of the two-dimensional problems that we have discussed in this lecture. So we have seen the derivation for the stiffness matrix considering the conduction, then the stiffness matrix considering the convection heat transfer, then we have studied the force vector or the load vector, then the calculation of the shape function. So all this formula we have discussed, and based on this different formula we have discussed two different problems. Okay, so this is the end for this lecture.